Gonna talk. He's also, until recently, he was with us.
Yeah.
And so he's still one of us. We'll just claim him. He's going to talk to us about the rush subsystem of the UNSW Echo.
Right, so Lance being too close, I'll just keep my distance. No one is stopping me. I might go over 10 minutes. I'm Ediz. I'll be talking about the rush payload. So until recently, I was with UNSW in Oxford. So just moved to Macquarie, and hopefully planning to start things up there as well in this domain. There's already some activity, but get it going. So I'll talk about the work that I've done with colleagues here, as well as the work that we're still carrying on collaborating as well. Also, when I was asked about to do this talk, so it was about the rush payload. But in my mind, rush payload is just a platform to test the research that we've been doing. So this is a journey we started back in late 2011, early 2012. So rush payload actually tests some of those research. So I'll touch on that. So I'll talk about the research aspects as well as the payload itself. I think the main motivation for us was making use of COTS field programmable gate arrays. So commercially available field programmable gate arrays that has the processing power that is needed for future systems. I guess the second bullet point, I'm talking to the converted here. There's a big drive for using low-cost nano and micro satellites, and I think the FPGAs, they fit the platform whereby you can deliver the grunt you need, and the power consumption is reducing further. So also the beauty of the SRAM FPGAs is that enables you to write Moore's law, whereby your radiation hardened ones or the flash-based ones are not as up to date as your latest SRAM-based FPGA. So the group that I belong to, I still collaborate with. We are basically looking into research into designing highly reliable systems, highly reliable reconfigurable systems for space applications. So the beauty of the FPGAs is that some of you may or may not know is that you're able to reconfigure them. So it's not like your application-specific integrated circuit whereby you just build it once and that's it. You're stuck with it. With the FPGAs, you can reprogram them on the fly. So in situ changes of the reconfiguration. So if you have a new algorithm that you want to run on it, you can just upload the bit stream from ground, and then the device changes its characteristics. And in our case, we are utilizing the reconfigurability to fix errors. So these are single event upsets and permanent errors that we have. So we are harnessing the power of FPGAs. And they are readily available. So some of the red hot ones might be ITAR restricted, so the COTS ones are available. So if you have a look at the drive to use FPGAs in space applications, so here's a snippet from the Sentinel-2 mission. So this is based from a report in 2012, looking at the number of FPGAs. So these are flush, so radiation tolerant, as well as SRAM FPGA. So if you look at it, the payload, actually 86% of the payloads utilize an FPGA of some sort. The platform, we have 53%. So overall, we're having 58% of the satellite consisting of FPGA, so flash and SRAM-based FPGA. So there's a big drive there. And then, as you can see, the A6 platform is 32%, and you have your standard, box standard A6 that you can buy, 5%. So yeah. So one of the, just a bit of an FPGA primer. So you can think about the FPGA as a two-layer cake. So the first one might be your application layer, where your user circuits live. So that does the functions that you want it to do. And then you have the configuration layer, which is underlined. So it's the configuration layer that you configure. You write your zeros and ones, or you download your bit stream, so-called, and then it configures the resources you have on the FPGA to do what you want. So you have the red part here is your application, so you have your routing happening there, you have a switch, you have a lookup table which you configure to the end operation, right? You have your memory elements and selectors. So by virtue of writing these, you change the application there. So the problem is that with FPGA, these are all SRAM based, right? And this SRAM is pretty large compared to other resources you have, and the SRAM is vulnerable to single event upsets, so your radiation effects out in space. So you have your deposited charges, so whereby you have a certain configuration, and all of a sudden you have an SU, single event upset, because of the radiation environment. A bit flips, and your routing changes, right? So in the application layer, basically you're no longer functioning the way you want, and your AND gate turns into an XOR, for example, right? So then you have, at the application layer, you might have some transient problems, right? So you have a certain logic operation happening, and you have a certain value, that changes, and then your function becomes 1. Now, with this type of error, they are here today, gone the next cycle, right? So they will just appear as a glitch, and the next cycle they are gone. But with these types of errors, unless you refresh the configuration memory, they're going to stay there. So they stay as permanent errors. So your circuit will be giving you a wrong result all the time, right? So it's not permanently damaged, physically permanently damaged, but basically your configuration has changed. So you're doing a function that you are not meant to. So there are ways of dealing with this. So the most commonly used one is what people call scrubbing. So you have your FPGA here. So one of the things I would like to do, there's a pointer. Let's see if I can use it. I would like to spend, this is a bit of a busy diagram, but the way people design fault-tolerant systems is what they use. They use triple modular redundancy, right? So you can have it either, you triplicate, so let's say M being the function that we want, you make 3 copies of it, you give the 3 inputs, and then at the end you basically vote, and the majority wins, right? So this way, if one of the units is giving you the wrong answer, the other 2 will overvote, and then you still get the right answer, right? So, but if you had a normal system, it wasn't on an FPGA, and this one goes down, there's no way of fixing it. But in FPGAs, you can actually fix it. So what we have here is the P stands for pins, so you have the pins of the FPGA or your IC feeding into your modules, they get voted upon, and it moves to the next layer. I will talk about these later on, so we have different configurations. So let's deal with this one. So what the scrubbing does is, you know the configuration layer that I talked about? It basically keeps on scrubbing, right? Keeps on rewriting. So it's a number of tens of megabytes depending on the size of your FPGA. So it basically keeps on scrubbing all the things, right? Write, write, and write. Now, if you don't have an error, you're doing this, you're wasting your energy. We have limited resources up there. So this way you're oblivious if you have an error or not, right? You just do it. Now, imagine that you have an error happening right after you scrub a part of the circuit. What will happen is that you won't pick that error up until you go all the way back up. So your mean time to detect errors is increased, right? So the mean time to detect is an important matrix that we use. But on the other hand, as an FPGA designer, I can go to, so you have your Xilinx, your Altiras, your microsemis, they provide you with special cores, but I can go drag and drop, and then it will do the scrubbing for me. So it's easy, right? So what we're trying to do is actually, is there a way of doing this in a much more energy efficient way, in a less resource wasting way? So given that the CUBESATs, we have limited resources. So, okay, there you go. Obviously, you're meant to see some errors happening and then it's fixing itself, but anyway, didn't work. Now, the approach that we've employed, And what will be tested on the rushboard is what we call modular error recovery. So what we mean by that is we rely on our voters telling us which one of the modules is in error, and we go and surgically just, this one worked. So let's see that again. So imagine that this module is in error from the voter we know, and we just basically surgically go and fix that module. And we utilize what in the terminology they call dynamic partial reconfiguration. So while the other two are still operating, we are able to go and fix them. So the system is still available, albeit it has reduced reliability. Now, the beauty of this is we are basically fixing the errors as they occur, and also we are able to detect them much faster. So if you look at this, the size of that M, the module, in the research that we are looking at, is something that as a designer you can specify. You can tell us that Ediz, we want our system to detect an error in so many milliseconds, so many microseconds. So we have the tools in place to actually resize that M and insert the voters for you such that you're able to detect the error and recover from it. So we are bounding the error recovery. So error detection and error recovery, so which affects your overall system reliability. Also, we are not scanning this gray area. You see, I told you, being too close to him is not good. So in this process, the gray area you see at the back is not scrubbed, right? So we are not wasting energy. We are not rewriting the bits that were there. Right, so the rush payload. So the rush payload, as you can see, I think I brought a dot version as well in my bag somewhere. We'll be testing the traditional scrubbing approach and our modular error recovery-based approach. So we have a Tealength Arctic-7 FPGA, it's an SRAM, and that was the largest FPGA that we could get, given the money we had. So at the end of the day, that's our sensor, and we want to be able to detect radiation up there, right? High enough to actually flip one of those bits. So we have a flash-based FPGA that does the talking to the onboard computer and oversees the experiment. So we are logging if an error has happened, how long it took us to recover from it, and so forth, and also the power consumption. So this is the board. Now the interesting thing comes. So we've done this, so we had all these deadlines, we prepared the payload, we said, okay, these are the experiments we're going to run, we locked them down, that's it, but the research didn't stop. And as you heard before, there were like 2 years of uncertainty, what's going on. So in the meantime, as a team, we carried on, and we had a question whereby, is there a way, so if you look at this side, over this slide, as you can see, we have your pins, right? Inputs coming in, triplicated modules, voters are triplicated themselves, everything is triplicated. But there might be cases whereby you cannot triplicate them because your FPGA is not large enough, or there are some resources on the FPGA that cannot be triplicated. You're stuck with them. So you have this more of a heterogeneous system rather than the homogeneous way that we have here, and that's what these two are trying to show. So here we have a single pin coming in, everything is triplicated, but this water is not triplicated. So how do you deal with this? So one of the things we came up with is what we call FMER, and as the name suggests, we have a frame-based recovery, so we are scrubbing as well as we are doing module. So basically we are scrubbing the gray area only, not the white blocks, and if there's an error detected in the module, we stop, we scan the module, and then we carry on. So I think these slides will be made available online, so if you want to look at it, we've published this in 2016, so I have my academic hat on now. The next one. Another thing we looked at is that you have all these modules, right? They all have their voters, and they are saying that, hey, there's something wrong with me, you need to fix me. So how do you go about achieving that? So you can say, okay, I'm going to be fair and I'll do in a round-robin fashion, I'll say, are you okay, are you okay, are you okay? Or I'm just going to come up with a more adaptive way of doing it. So we had a look at dynamically scheduling the time at which we check the voters, and we've shown that that has a great impact on your system reliability. The next thing, how are you going to communicate the results or the requests from the modules to the brains, right? So you have your reconfiguration controller that oversees this. So you can either use the application layer, but then that will suffer from the SEUs, or you can use the configuration layer. So there's already an inbuilt mechanism. On the Xilinx term, it's called the ICAP port that links the application layer to the configuration, and then you're able to go this way and then check those things. So using this, you're increasing your reliability. So once again, more details, you can find them in this paper. So we've evaluated for different altitudes and radiation environments how these behave. So it's telling me to wrap up. I have a couple of more slides to go. Now, the next thing, one of the things when we started doing this thing, all this breaking, so you give me a circuit, it just does A plus B, then we need to take that, triplicate it, put the waters in. All these things, so the ones on the rush bar, they were all done manually. It takes quite a bit of time, it's a pain in the backside. So now, to deal with that, this is hot off the press, and it's going to be presented in May and demonstrated in May in the US, is what we call a Tealength, whereby most of you might have applications written in C at a high-level language, and you just give us that, and we run it through the Tealength process, which generates triplicated design for you with the waters inserted based on your requirements in terms of how fast you want this to detect errors and recover, and then it will give you an FPGA-ready code. So then you can just download that and off you go. So we've started that process now. So hopefully you will have the demo at the FCCM. All of this wouldn't have been possible without a great team. So we had a lot of honors thesis students, summer research students, PhDs, postdocs, masters by research students. So here is the team, or part of the team, when the EcoZero got together. So there is me, a bit smaller profile of the belly, my partner in crime, Oliver Diesel from School of Computer Science. So we started this journey, as I said, late 2011. We managed to secure 15K from Faculty of Engineering, and then all of this came from there. Tom, he's looking at the first PCB of the rush board. So he did this as part of his honors thesis, fourth year student. So the PCB we have is based on his design. We have Nguyen, who is here. We have Dimitris, these are our PhD students. We have William, he's a fourth year student now. We're looking at the OBC interfacing and looking after the hardware. We have Raymond, masters by research student, he finished. And
the talk is finished.
And the talk is finished. Well,
thank you.
Okay. Funding, I would like to thank the ARC. We've been successful in securing a linkage and a discovery grant. So we are working with Thales Alenia Space and General Dynamics New Zealand. And the last one, what's next for Rush? Basically, we are launching Rush in Brazil. That's the last slide it has. We are launching Rush later on this year as part of a collaboration with a Brazilian partner. And as you can see, the Southern Cross there and the map of Brazil. So that's going to be a 1U CubeSat, and it's going to 700 kilometers, which we are hoping that we'll see more SEUs happening, because at 400, I guess, apart from the South Atlantic, I don't know what we're going to see. And we have a software-defined radio version of it happening, looking at 7 to 6 gigahertz operation. So we want this to be, in a nutshell, to be the Hawkeye in space. And from you, what do we need from you is we are always looking for use cases. So if you have any applications that you want to accelerate on FPGAs, you want to run on FPGAs, be it any level of description it is in, C, MATLAB, VHDL, please do get in touch. These are great benchmarks for us, and it also drives our research. So I think that's all I want to say. Sorry that I went over time, but there's a bit of quite a lot of things. So I just didn't want to just talk about the payload itself, but the research behind it and the team that's behind it.
Please thank Ediz.